In mathematics, specifically category theory, adjunction is a possible relationship between two functors. Adjunction is ubiquitous in mathematics, as it specifies intuitive notions of optimization and efficiency. In the most concise symmetric definition, an adjunction between categories C and D is a pair of functors, and in a family of bijections which is natural in the variables x and y. The functor f is called a left adjoint functor, while g is called a right adjoint functor. The relationship, f is left adjoint to g, is sometimes written this definition and others are made precise below. Introduction. The slogan is, adjoint functors arise everywhere. The long list of examples in this article is only a partial indication of how often an interesting mathematical construction is an adjoint functor. As a result, general theorems about left-right adjoint functors, such as the equivalence of their various definitions or the fact that they respectively preserve colimits, limits, can encode the details of many useful and otherwise non-trivial results. Spelling. One can observe two different roots are used, adjunct and adjoint. From Oxford Shorter English Dictionary, adjunct is from Latin, adjoint is from French. In Maclane, Categories for the Working Mathematician, Chap. 4, Adjoints, one can verify the following usage. The Homset bijection is an adjunction if an arrow in is the right adjunct of the functor is left adjoint. 4. Motivation. Solutions to optimization problems. It can be said that an adjoint functor is a way of giving the most efficient solution to some problem via a method, which is formulaic. For example, an elementary problem in ring theory is how to turn a Rng into a ring. The most efficient way is to adjoin an element 1 to the Rng, adjoin all the elements which are necessary for satisfying the ring axioms, and impose no relations in the newly formed ring that are not forced by axioms. Moreover, this construction is formulaic in the sense that it works in essentially the same way for any Rng. This is rather vague, though suggestive, and can be made precise in the language of category theory. A construction is most efficient if it satisfies a universal property, and is formulaic if it defines a functor. Universal properties come in two types: initial properties and terminal properties. Since these are dual notions, it is only necessary to discuss one of them. The idea of using an initial property is to set up the problem in terms of some auxiliary category E, and then identify that what we want is to find an initial object of E. This has an advantage that the optimization, the sense that we are finding the most efficient solution, means something rigorous and is recognizable, rather like the attainment of a supremum. The category E is also formulaic in this construction, since it is always the category of elements of the functor to which one is constructing an adjoint. In fact, this latter category is precisely the comma category over the functor in question. The morphisms in E between Rs1 and Rs2 are commutative triangles of the form where S1, S2 is a ring map. Note that this is precisely the definition of the comma category of R over the inclusion of unitary rings into Rng. The existence of a morphism between Rs1 and Rs2 implies that S1 is at least as efficient a solution as S2 to our problem. S2 can have more adjoined elements or more relations, not imposed by axioms, than S1. Therefore, the assertion that an object RR** is initial in E, that is, that there is a morphism from it to any other element of E, means that the ring R** is a most efficient solution to our problem. The two facts that this method of turning Rngs into rings is most efficient and formulaic can be expressed simultaneously by saying that it defines an adjoint functor. Symmetry of optimization problems. Continuing this discussion, suppose we started with the functor f, and posed the following question. Is there a problem to which f is the most efficient solution? The notion that f is the most efficient solution to the problem posed by g is, in a certain rigorous sense, equivalent to the notion that g poses the most difficult problem that f solves. This has the intuitive meaning that adjoint functors should occur in pairs, and in fact they do. But this is not trivial from the universal morphism definitions. The equivalent symmetric definitions involving the junctions and the symmetric language of adjoint functors have the advantage of making this fact explicit. Formal definitions. There are various definitions for adjoint functors. Their equivalence is elementary but not at all trivial and in fact highly useful. This article provides several such definitions. The definitions via universal morphisms are easy to state, and require minimal verifications when constructing an adjoint functor or proving two functors are adjoint. They are also the most analogous to our intuition involving optimizations. The definition via Counit unit adjunction is convenient for proofs about functors which are known to be adjoint, because they provide formulas that can be directly manipulated. The definition via Homset makes symmetry the most apparent, and is the reason for using the word adjoint. Adjoint functors arise everywhere, in all areas of mathematics. Their full usefulness lies in that the structure in any of these definitions gives rise to the structures in the others via a long but trivial series of deductions. Thus, switching between them makes implicit use of a great deal of tedious details that would otherwise have to be repeated separately in every subject area. For example, naturality and terminality of the Counit can be used to prove that any right adjoint functor preserves limits conventions. The theory of adjoints has the terms left and right at its foundation, and there are many components which live in one of two categories C and D which are under consideration. It can therefore be extremely helpful to choose letters in alphabetical order according to whether they live in the left-hand category C or the right-hand category D, and also to write them down in this order whenever possible. In this article, for example, the letters X, F, epsilon will consistently denote things which live in the category C. The letters Y, G, eta will consistently denote things which live in the category D, and whenever possible such things will be referred to in order from left to right. Universal morphisms. A functor f, CD is a left adjoint functor if for each object x in C, there exists a terminal morphism from f to x. If for each object x in C, we choose an object GOX of D for which there is a terminal morphism epsilon x, fx from f to x, then there is a unique functor G, CD such that Gx equals GOX and epsilon x fg equals f epsilon x for EF. XX a morphism in C, F is then called a left adjoint to G. A functor G, CD is a right adjoint functor if for each object Y and D, there exists an initial morphism from Y to G. If for each object Y and D, we choose an object FOY of C and an initial morphism A to Y, YG from Y to G, then there is a unique functor F, CD such that Fy equals FOY and GF to Y equals A to YG for G. YY a morphism in D, G is then called a right adjoint to F. Remarks. It is true, as the terminology implies, that F is left adjoint to G if and only if G is right adjoint to F. This is apparent from the symmetric definitions given below. The definitions via universal morphisms are often useful for establishing that a given functor is left or right adjoint, because they are minimalistic in their requirements. They are also intuitively meaningful in that finding a universal morphism is like solving an optimization problem. Counit unit adjunction. A Counit unit adjunction between two categories C and D consists of two functors f, CD and G. CD and two natural transformations respectively called the Counit and the unit of the adjunction, such that the compositions are the identity transformations 1f and 1g on f and g respectively. In this situation we say that F is left adjoint to G and G is right adjoint to F, and may indicate this relationship by writing, or simply, in equation form, the above conditions honor the Counit unit equations, which mean that for each x in C and each y in D. Note that here denotes identity functors, while above the same symbol was used for identity natural transformations. These equations are useful in reducing proofs about adjoint functors to algebraic manipulations. They are sometimes called the zigzag equations because of the appearance of the corresponding string diagrams. A way to remember them is to first write down the nonsensical equation and then fill in either F or G in one of the two simple ways which make the compositions defined. Note: the use of the prefix co in Counit here is not consistent with the terminology of limits and colimits, because a colimit satisfies an initial property whereas the Counit morphisms will satisfy terminal properties, and dually. The term unit here is borrowed from the theory of monads, where it looks like the insertion of the identity 1 into a monoid. Homset adjunction. A Homset adjunction between two categories C and D consists of two functors F, C, D and G, CD and a natural isomorphism. This specifies a family of bijections for all objects X in C and Y in D. In this situation we say that F is left adjoint to G and G is right adjoint to F, and may indicate this relationship by writing, or simply. This definition is a logical compromise in that it is somewhat more difficult to satisfy than the universal morphism definitions, and has fewer immediate implications than the Counit unit definition. It is useful because of its obvious symmetry, and as a stepping stone between the other definitions. In order to interpret phi as a natural isomorphism, one must recognize HOMC and HOMD as functors. In fact, they are both bifunctors from DOP times C to set. For details, see the article on Hom functors. Explicitly, the naturality of phi means that for all morphisms F, X, X in C and all morphisms G, Y, Y in D, the following diagram commutes. The vertical arrows in this diagram are those induced by composition with F and G. Formally, HOM, HOMC is given by HFO HOFG for each H in HOMC. HOM is similar. Adjunctions in full. There are hence numerous functors and natural transformations associated with every adjunction, and only a small portion is sufficient to determine the rest. An adjunction between categories C and D consists of a functor F, CD called the left adjoint, a functor G, CD called the right adjoint, a natural isomorphism phi, HOMC HOMD, a natural transformation epsilon, FG1C called the Counit, a natural transformation eta, 1DGF called the unit, an equivalent formulation, where X denotes any object of C and Y denotes any object of D. For every C morphism F, Fyx, there is a unique D morphism phi Y, X equals G, YGX such that the diagrams below commute, and for every D morphism G, YGX, there is a unique C morphism phi minus 1 Y, X equals F, Fyx in C such that the diagrams below commute. From this assertion, one can recover that the transformations epsilon, eta, and phi are related by the equations. The transformations epsilon, eta satisfy the Counit unit equations. Each pair is a terminal morphism from F to X in C. Each pair is an initial morphism from Y to G in D. In particular, the equations above allow one to define phi, epsilon, and eta in terms of any one of the three. However, the adjoint functors F and G alone are in general not sufficient to determine the adjunction. We will demonstrate the equivalence of these situations below. Universal morphisms induce Homset adjunction given a right adjoint functor G, C, D. In the sense of initial morphisms, one may construct the induced Homset adjunction by doing the following steps. Construct a functor F, CD and a natural transformation eta.
For each object y and d, choose an initial morphism, eta y, from y to g, so we have eta y, yg. We have the map of f on objects and the family of morphisms eta. For each f, y0, y1, as eta y0 is an initial morphism, then factorize eta y1 no f with eta y0 and get f, ff. This is the map of f on morphisms. The commuting diagram of that factorization implies the commuting diagram of natural transformations, so eta 1 dGOF is a natural transformation. Uniqueness of that factorization and that G is a functor implies that the map of f on morphisms preserves compositions and identities. Construct a natural isomorphism phi, HOMC for each object x in C, each object y and d, as eta y is an initial morphism, then phi y x is a bijection, where phi y x x equals GO eta y. Eta is a natural transformation, G is a functor, then for any objects x0, x1 in C, any objects y0, y1 in D, any x. x0, x1, any y, y1, y0, we have phi y1, x1, equals GO eta y1 equals GO eta y0 y equals GO phi y0, x0 y, and then phi is natural in both arguments. A similar argument allows one to construct a Homset adjunction from the terminal morphisms to a left adjoint functor. Counit unit adjunction induces Homset adjunction given functors f, c, d, g, c, d, and a Counit unit adjunction, f, g. We can construct a Homset adjunction by finding the natural transformation phi, HOMC, HOMD in the following steps. For each f, yx and each g, ygx, define the transformations phi and psi are natural because eta and epsilon are natural, using, in order, that f is a functor, that epsilon is natural, and the Counit unit equation 1 fy equals epsilon fyof, we obtain. Hence psi phi is the identity transformation. Duly, using that G is a functor, that eta is natural, and the Counit unit equation 1 gx equals GO eta gx, we obtain. Hence phi psi is the identity transformation. Thus phi is a natural isomorphism with inverse phi minus 1 equals psi. Homset adjunction induces all of the above given functors f, c, d, g, c, d, and a Homset adjunction phi, HOMC, HOMD. We can construct a Counit unit adjunction, which defines families of initial and terminal morphisms, in the following steps. Let for each x in C, where is the identity morphism? Let for each y in D, where is the identity morphism? The bijectivity and naturality of phi imply that each is a terminal morphism from f to x in C, and each is an initial morphism from y to g in D. The naturality of phi implies the naturality of epsilon and eta, and the two formulas for each f, yx and g, ygx. Substituting fy for ex and eta y equals phi y, fy for g in the second formula gives the first Counit unit equation, and substituting gx for y and epsilon x equals phi minus 1 gx, x for f in the first formula gives the second Counit unit equation.